A heating curve is essentially a graph of temperature versus heat. In other words, as we add heat to a specific substance, how does its temperature change? This gives us important information about boiling points, melting points, enthalpies of specific phase changes, as well as specific heat capacities of the solid, the liquid, and the gas. I really like heating curves. I think your understanding and your ability to explain a heating curve really fundamentally gets at your basic understanding of thermodynamics. Now, in this class, we will limit ourselves to heating curves that represent constant rate and constant pressure, and we'll also limit ourselves to substances that have only one liquid, only one gas, and only one solid phase under the temperature and pressure conditions that we're looking at. The unattractive heating curve that I've drawn for you here represents the heating curve for 1 mole of water. This is the same as the slide or the image that's shown on slide 9 in your lecture notes. What we have is temperature on the y-axis in degrees Celsius versus heat added, and I've made a note here. This should actually be kilojoules per mole, but I've taken care of that by adding the 1 mole notation over here on the side. So even though I've not put in any numbers, as we move from left to right, we're adding heat in kilojoules. Now, this is for water, and so hopefully you recognize the 0 and 100 degrees Celsius marks that I've put on here as the melting point MP and the boiling point BP, respectively, for water. So if we started at a temperature less than 0, we're effectively starting with the solid of water, or ice, in other words. And as we add heat to the solid, we actually are causing its temperature to increase. Now notice that the slope of this line is very steep, and that indicates that it really doesn't take very much heat to heat up this 1 mole, or to cause a big temperature change for this 1 mole of ice. If you think about it, that really is going to correlate to the specific heat capacity of the ice, and we'll talk more about that in a moment. We can heat up that ice until we get to the melting point, or 0 degrees Celsius in this case. At that point, if we continue to add heat, all of the heat added is going to be used to overcome the intermolecular forces in the solid to turn it into a liquid. In other words, this plateau represents melting. Remember, there's no temperature change associated with any phase change, again, because we're using all of the heat that we add to overcome the intermolecular forces in our particular substance. Once we've melted all of our ice, however, we can then start to heat up our resulting liquid. Notice that the slope of this line is quite different than that for the solid, indicating that the solid and the liquid have different specific heat capacities. We can continue to add heat, and the temperature will continue to increase until we get to the boiling point at 100 degrees Celsius, and then we have another plateau. Now notice this plateau is much longer than the melting plateau. This plateau represents evaporation or vaporization. Notice that for the same 1 mole of water, it takes a lot more energy to evaporate 1 mole than it does to melt 1 mole. This indicates that the delta H of vaporization for water is much larger than the delta H of fusion, or the delta H of melting. Once we evaporate the water, we have everything into the gas phase, and we can heat that gas up by continuing to add heat. Again, notice that the slope of the line is different than it was for the solid and the liquid, and this again indicates something about the amount of energy required to heat that 1 mole of gas versus the amount of energy required to heat the liquid or the solid. Before we go any further though, let's go ahead and put in something that I think is really important. As we add heat from left to right, we go from the solid to the liquid to the gas. Those phase changes, melting and evaporation, or even sublimation going from the solid straight to the gas, all are endothermic processes. We have to put heat into the system to make them happen. If we were to take our heating curve and come back in the other direction, however, making it effectively a cooling curve, then we can see that when we go from the gas to the liquid, in other words condensation, or the liquid to the solid, in other words freezing, or the gas to the solid, deposition, all of those processes are exothermic. We're going to be able to tie this into something called Gibbs free energy and entropy a little bit later. Now let's go back to these ideas of delta H of a phase change and the specific heat capacity for a specific substance respectively. Let's start with specific heat capacity. If you think about it, the units on a C sub P, or specific heat capacity, are usually joules per gram or joules per mole if we're doing molar heat capacity, times some temperature change, right? Degrees Celsius or Kelvin. Well, if we look at the slope of these lines, assuming we're moving in the forward direction, rise over run is slope, and that actually gives us our slope, in this case, is temperature divided by joules per mole. So it's actually upside down. So really what we can say is that the slope of each individual line is equal to 1 over the specific heat capacity, or in this case the molar heat capacity for that particular substance. Where I just marked on the graph, for example, would be 1 over the molar heat capacity, for the liquid. 1 over the slope here would be the molar heat capacity for the gas, and 1 over the slope down here would be 1 over the heat capacity for the solid. And so we can make comparisons of those values relative to one another. If you look at the slide in your lecture notes, you'll see that our phase changes, our plateaus, are actually marked with some values. So from here to here, it's marked as 6.01, meaning 6.01 kilojoules added per mole of water. The delta H of fusion then, that's an S, fusion, is actually 6.01 kilojoules per mole. If we look from here to here, that's 40.67 kilojoules, and that actually does represent the delta H of vaporization for water. The delta H of sublimation is not easy to derive from this particular line or from this particular graph. You can't get to it specifically just by looking at the graph. So these are all very important facets of the graph that I think are really important for you to be able to identify. Ultimately, I want you to be able to look at a graph like this and explain it to someone else. This is actually in your lecture notes the exact same slide, or the exact same graph shown on the previous slide. We just want to take a moment to mark some of the important places where we can correlate a calculation to places on the graph. So as a shorthand, I'm going to denote places where there's a slope versus places where there is a plateau. Places where there is a slope, we're looking at heating or cooling. Places where there's a plateau, we're looking at a phase change. If we go back and think about the calculations that we've done in the past, we know how to calculate Q for a heating or a cooling. We use mass times specific heat times delta T, or moles times molar heat capacity times delta T. Remember, when there's a phase change, there is no temperature change associated. So to calculate the heat associated with the phase change, we just multiply the number of moles by delta H for that particular phase change. Be really careful when you do either one to make sure that you've grabbed either the specific heat capacity or the molar heat capacity for the right phase, and that you've grabbed the delta H for the correct phase change. We'll do an example on the next slide. Before we jump into this problem, I want to go ahead and make the note that if we do a calculation like this for any substance other than water, I'll provide the boiling points and the melting points. I don't expect you to know those for anything other than water. When you're doing something other than water in particular, it's very handy to start with a little number line. I'm going to go ahead and do it here. I start by putting in my boiling point and my melting point. Boiling point listed second in this case. And then I mark where we're starting. So we're starting at 50 degrees Celsius, and we're going to go to 120 degrees Celsius. The reason that I've done this is because it helps me keep things straight. I know that below 0 I have a solid, above 0 but less than 100 I have a liquid, and above 100 I have a gas. So in this case, I'm starting with a liquid, and the first thing that I need to do is heat it up from 50 degrees to 100 degrees. At 100 degrees, I can do a phase change. I can evaporate my liquid. And then I need to take my resulting gas and heat it up from 100 degrees to 120 degrees. So I'm going to have 3 phases to my particular problem. If you think about it, this type of problem could be anywhere from 1 step to 5 steps, depending on where you start and where you stop. Let's start by calculating the amount of energy required to heat the liquid from 50 degrees to 100 degrees. A couple of important things to note here. Usually specific heat capacities are given in joules per gram degree Celsius. In this case, in an effort to be nice, we actually gave you the delta H of vaporization in kilojoules per mole, which is typical, and then went ahead and gave you the specific heat capacities in joules per mole degree Celsius instead of joules per gram degree Celsius so that you didn't have to do the conversion. Be really careful about this. Usually these specific heat capacities will be in joules per gram, and you have to pay attention to which version of which equation you're using. Here, my 27.75 moles I found simply by taking the 500 grams of water and using the molar mass of 18.01 grams per 18.02 grams per mole to convert. So let's just make a quick note that the 500 grams are equal to 27.75 moles. Okay, so I've calculated that the amount of heat required to heat the 500 grams of water from 50 degrees to 100 degrees is 1.045 times 10 to the 5th joules. Now I'm ready to calculate the heat associated with evaporating that same 500 grams or 27.75 moles of water. By taking the 27.75 moles of water and multiplying by the delta H of vaporization, 40.7 kilojoules per mole, I got 1129 kilojoules or 1.129 times 10 to the 6th joules. At this point, we've heated our water from 50 degrees to the boiling point of 100 degrees, and now we've evaporated that water. We're left with gas at 100 degrees. Finally, we need to convert that steam to 120 degrees, or heat that steam, from 100 to 120 degrees. We use the same process as in step 1, but this time our our specific heat capacity or molar heat capacity is different. We're using the one for the gas, and our delta T is only 20 degrees. So now we have 3 different values, and to find the total amount of energy required for this process, we just add them all. We get 1.25 times 10 to the 6th joules. You can tell that the vast majority of the heat required for the process actually comes from the evaporation portion, which is pretty typical.